Yeah, no, I said we weren't having class on Monday, not today. Monday. Right, so we all remember, right? No class Monday. Well, no, this class on Monday. Uh, uh-huh. All right, well, let's get to it. So, one kind of change I wanted to make from last time, I thought about the issue that we had, and there's a relatively easy fix. So, last time we made the decision to number the disks so that the biggest disk is the one at the bottom. Or well, duh, of course the biggest disk is the one at the bottom. That's something I meant. The biggest disk was number n, right? So if we had 5 disks, the big one's number 5. Um, it was a 50-50 shot, and if we stick with that, then the sort of recursive function that I want to define will have to uh, we will have to add in another parameter, another argument for the number of the biggest disk. Well, that adds another thing. Okay, so let's actually redo it, redo this sort of argument, but this time let's do it where we make disk number n the smallest disk. And so disk number 1 is always the guy at the bottom. Okay, so is that okay, first off, right? We could have made the either choice last time, um, but I want to go back and choose the other way. All right, so if we do that, um, then what's the recursion going to look like? Well, the list of things that we wrote last time, the list of instructions, if all it is move, 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 then basically they're still going to be the same with the exception that we flipped the numbering. Okay, so what would it be if I was doing 3 disks? Well, actually, let's start with 2 just for sake of simplicity. So, what was the sequence of moves if we had 2 disks? Now, keep in mind here, I'm going to label disk number n the small one, not the big one. Yeah. Okay, so it'd be 2 in this case. So if I'm gonna renumber it so that the top disk is number 2, not number 1. Right. A B. Okay, and then okay, oops. Okay, so if we just had 2 disks, that's what we would have. Okay, and again, this is exactly the same as what we had last time, with the one exception that I've flipped the order of the numbering. Just and you guys, I think, will see in a minute why that's convenient. Okay, all right. So what is it if we have 3 disks? Well, we need to move, oops, 3 from where to where? Okay. Oh, and you guys on the at home can't see this because I'm a giant idiot. We switch the source, and hopefully that'll work. Uh, Camden, that makes sense. Uh, uh, okay, so hopefully Adam will pop up, and you guys will be able to see this. Let me make sure that it's. Oh no, of course not. This one. Okay, there we go. So now everybody at home can see too. All right, so we need to move 3 from where to where. Let me actually let me do a full screen uh, and see if it's going to cooperate this time. Um, okay, so those of you who are at home hopefully can see 2 things. Yes, okay, good. All right, so on the left I've got the Towers of Hanoi, just so we've got the reference, and on the right I've got my the stuff we're going to write. Okay, so what's the idea here? in order to solve the 3-disk problem, we need to move the top 2 from A to B to get them out of the way. Then we can move the very bottom one to C, and then we can move the top 2 back onto B. All right, so in order to do that, I need to move disk number 3, which is the smallest one, over to C, then disk number 2 to B, then I can move disk number 3 from C back to B. Okay, that means that now the big one at the bottom is open, so I can move him from A to C. And then finally, I just need to reverse the process. And now I'm moving these top 2. They're sitting at B. I need to move them to C. So step 1 is move 3 from B to A. Okay, so that gets him here. Okay, then I need to move 2 from B to C. And finally, I need to move 3 from A to C. Okay, so move 2 there and move 3 there, and we've got it. Okay, so let's look at what we've got. These 3 and those 3 have the same kind of pattern that we saw before, right, in terms of where the letters are. And instead of it being, 1, 2, 1, this time it's 3, 2, 3 because we just reordered the numbering in the other order for convenience. Okay, and but notice that the little chunks of 3, and I spaced it so that it was obvious, don't they look a whole lot like the 2-disk case? Okay, now they're not identical because instead of 2, 1, 2, we have 3, 2, 3. Okay, so there's that, but well, and the letters are somewhat permuted, right? So A's, B's, and C's have kind of gotten jumbled up, but they've been jumbled up in a very sensible way, right? Okay, so do we kind of see the structure then? Okay, so what this means is what we can do is sort of, as a mathematician might say, we'd go in for the kill at this point. All right, and so let's define the general function. All right, so I'm going to make a function, and I'm going to say that this takes in the number of disks and 3 things. It's going to take in the name of the start peg, the name of the end peg, and the name of the temporary peg. Okay, so in most cases, what will that be? Where's our start peg? A. Where's our end peg? C. And then the dude that we used as temporary was peg number or peg letter B. Okay, but as we'll see, that's not always going to be the case. All right, so here's why I wanted to renumber it. And I'm going to write this in sort of Python style syntax. All right, so here's why I wanted to renumber it, because it makes this convenient. When's the situation that we're always moving a single disk? Well, if we're moving a single disk, what's the disk number? 1, right? Because we chose to put, for today, we chose to put 1 at the bottom, not at the top. And so right here, all I have to say is move 1 from start to end. Start peg to end peg. Okay, and the other thing is that the move instruction doesn't actually need to know what the temporary peg is because it doesn't use it, right? It's only in the recursion that we need this temporary thing. Yes? not in others. No, no, it doesn't matter. It just means that you just have to be, once you pick the name for a variable, you have to stick with it, obviously. But, yes, okay, good point. The two equal signs. Yeah. So I think we mentioned this a few days ago, but so the equal symbol is in math, like in human math. You guys, we use the equal symbol in two different ways. Okay, because you say something like let x equal 5, but then you also say something like x squared plus 2x plus 1 equals 0. Well, equals in both of those situations mean two different things. In the first instance, saying x equals 5, what you're doing is you're saying let the value of the variable x be 5. In the second instance, you're defining an equation. Okay. Now, because you guys are human, this isn't a big deal, right? You understand um, the nuance and the context. The computer, however, does not. So, in pretty much every computer language that I know of, if you want to assign the value of a variable, you use a single equal. Okay, so if I have a variable called num eggs, I would say num eggs equals 12. Single equals. Okay. If I want to check to see is the number of eggs equal to something, then I have to use double equals. So that's the difference. Okay. Um, yeah, and for sake of completeness, Mathematica is the same way. If you, how many of you guys have used Mathematica? I mean, Cole, I know you're using it because you're in calculus with me, but it's the same thing there. If you want to set the value of a variable, you use a single equal. If you want to use like the solve routine to do algebra for you, then it's double equal. Um, okay, so are we cool with that little detail? Yeah. Okay, so if there's more than one disk to be moved, then what do we need to do? Well, let's look at what we did up above. If there's more than one disk to move, then you move, um, you've got to move. So, like, let's say you've got 4 disks to move. Okay, how can we think about that? Well, let's take the top 3 and move them, then move the bottom one, then move the top 3. Okay, and so what we would have here would be Hanoi of. All right, so let me go over here and let me reset this and make it for 4 disks just for picture's sake. Okay, so the way I want to think about this is now I can't just pick up 3 disks at a time and move them. Okay, that's not according to the rules. However, could I sort of think about, can I move 3 disks from one place to another? Yeah, I have to do a whole bunch of rigmarole, but can I consolidate all of that into one operation, realizing that it's really multiple moves inside? Yeah, okay. So if I want to solve the 4 disk case, the first thing I need to do is move these top 3 to the middle peg to get them out of the way. All right, now how do I do that? I've got to do, this thing here and so on. But I can consolidate that into one thing. And what is that one thing? I want to move how many disks? Well, if I'm doing the 4 case, what is the number of disks? 4. Okay, so how many do I want to get out of the way? 3, which is the number of disks minus 1, right? All but the bottom. Now, where am I moving them from? I'm moving them from the start peg to where? The temporary peg. And who am I using as my temporary storage space? C, which is the ending peg. Okay, I know that seems funny. Okay, so what I mean by that is, here, let's move those 3 disks. Okay, how am I going to move them I've got to do him here, him here, him here, then this dude, and this dude back to there, then this guy here, and that guy there. So who was I using as my temporary peg? I was actually using peg C for most of that, not B, okay? And here's maybe the better way to put it, is where do I want those 3 disks to end up when I'm finished with that step? I want them to end up at not wherever the ending peg is, because I want the ending peg to be free to then move the big dude. Yeah? Okay. All right. And then what do I need to do? Well, I need to move the single disk, okay, which would be 1 from start peg to end peg. Okay, so that would be the move the dude at the bottom. All right, then what? Now I have to take, so now I'm in the situation like here. Okay, what do I need to do next? Well, these 3 need to get moved from where to where via where. They need to go from the temp peg to the end peg by using the start peg. Okay, so that'd be Hanoi, num disks minus 1. They're sitting at the temp peg. We want to end at the end peg, and we need to go via the start peg. Okay. Let me expand this slightly so that it's not cut off. Okay, so if we had, see, this is where this gets fun. Let's say we have 4 disks. How am I thinking of this? Well, do we have 1 disk? No, we have 4. Okay, so we're down here. So I'm going to move 3 guys out of the way. Then I'm going to just move the dude at the bottom. Then I'm going to move the 3 guys at the top. Okay, but notice that the Hanoi function refers to itself. So if I want to move 3 disks, how do I do that? I move 2, I move 1, I move 2. But how do you move 2? Well, you move 1, you move 1, you move 1. Okay, so do you see how this kind of unwraps like an onion? Yeah? Okay, so let's make sure we're clear with the algorithm here, and then I'm going to show you I've programmed this with a few extra little details in Python just to kind of show us that we do in fact get the correct sequences of instructions. Okay, so question, preguntas, fragen. All right, so let's take our set of instructions here, and I've got a separate version of this that's almost identical. The only difference is that I put in print statements so that it'll actually display the instructions for us. But other than that, it's structurally the same. Okay, and that would be this dude right here called Hanoi Pi. Okay, so this basically is what we had before, except like I said, instead of move, I've actually just printed the actual instruction with the word move. Okay, so that's the only difference, is that it's just printing stuff instead. All right, so let me pop open a console so we can run this. And that is not what I wanted. I wanted this one. Okay, so let's go to Dropbox, Wabash, Teaching, CSC101, Spring 20, Python. All right, so what I need to do is Python 3, and then I'm going to include Hanoi.py. Oh, damn it. Import. Damn it. Okay. It's going to be one of those sorts of mornings. Okay, fine. We'll just do it this way. Okay, so if I have exactly one disk, then this would be, I would want to run the program Hanoi of 1, starting at A, ending at C, using B as temporary. Okay, there's exactly one instruction to do that. You just pick up the disk and move the thing, right? And you're done. All right, now, if I did 2 disks, be this. 3 instructions. Let's double check that they're correct. Move 1 from A to B. Okay, that gets the um, yeah, top disk to the temp peg. Then move the dude at the bottom. Then move the. You know what, guys? I think I actually did the numbering back the way we did it last time. Oh, this is. It's a good thing it's Friday. Okay, whatever. It works. Um, so, all right, let's do the 3 disk case. All right, 1, 2, 1, 3, 1, 2, 1. Okay, so I guess basically just ignore everything I said up until this minute. So, okay. Yeah, that was silly of me. Sorry. Okay, so this program I wrote here uses the number. I picked a reordering and then promptly ignored it. Okay, so I realize this is super confusing now because, um, yeah, okay. Um, all right, so what's the salient point? Do we see the recursive structure here, right? That you do a thing, then it's a move in the middle, and then you do a thing? Yeah? Okay. And are we getting the set of instructions that we had before? Well, from say last time? Okay, like that. Okay, so we good? Yeah. All right. And Owen, how many did you end up doing it for at the end? 8? Okay, which would be 2 to the 8th minus 1. What is 2 to the 8th? Excuse me. 512, yeah. Is it 512? Yeah. 256. Yeah, it's 256, not 512. What do we do? Do you even math? No. Yeah, 256. Okay, so doing this with 8 disks requires 255 moves. Okay. Now, what would happen if I put in, what was it, 1,000 disks that we talked about? Right? I'm not going to do that because what's going to happen? Well, actually, it'll be worse than that. So, the Python has some protection stuff built in, right? Which which is that if you try and do too much recursion, it's going to say, nope, I'm not letting you do that much recursion. And that's essentially what just happened here, is that we hit the maximum stack depth of recursion, and so nothing actually ran because it said, nope, I'm not doing it. You just tried to get me to recurse too much. So, if I did something like, use the correct keyboard here, even something like, well, let's see how far we can push it. All right, so it'll do 64. Oh, is that what it said? I mean, I'd have to scroll back up now, but okay, it's doing 64. Yeah, this may take a while. Well, because how many moves is this? Well, 2 to the 64 is what? A lot, right? It's, well, what was it? It was like 1.8 times 10 to the 19th. Okay. Yeah. Well, I mean, it's still running, right? Like it's not finished yet. And well, let's see. If it takes, if that were a number of seconds, then that would be, so if it was, yeah, okay. So if it does one operation per second, which obviously it's going to do faster than that, then this is going to take 5 times 10 to the 11th years. Okay, so a long time. And we could probably see what's using considerable energy, the terminal, right? Okay, so I'm going to kill this because otherwise we'll be here. We'll be here for quite a while, okay? But, even if I did something like, let's say 16, right? Okay, that finished pretty quickly. So let's see if 32 finishes before class ends. Right, so 32, 2 to the 32 is like 4 point something billion, right? And so if this takes a second per operation, then we'll be here for 4 billion seconds, which is a long time, right? I guess this just, if this anything, this gives you a sense for how big exponential growth gets very quickly, right? Okay, but there it is, right? Yeah, so anyway. All right, so while that's running, let's see if it ever finishes. Let me pop open a Safari here because I did get or actually, Chrome's better. Well, and we already had Chrome open, so let's do Chrome's, just Chrome. Come on, OBS. And actually, you know what? For giggles, oops, that's not what I wanted. I wanted here. Let's see how much CPU Python is taking. Python is currently fully consuming 1 core of my processor. Big shock, right? Because it's doing its thing and it's still doing its thing. Okay. I think you guys get the idea, right? That's going to take a while. So let's actually go to Wikipedia here. Okay. And okay, whatever, right? Wikipedia is there's sort of a nice recursive picture. I like the way they do that. But a couple of people asked me actually about variations on this puzzle. Okay, so I thought I'd show you guys some of those because they're interesting. Okay. so there's lots of variations of this, okay? Um, and one of them that's kind of interesting is instead of thinking of the pegs being in a line, think of them as being on a circle, and you can only move either clockwise or counterclockwise, okay? Which is kind of interesting. Um, and then let's see, there's versions of this where you have more pegs. Okay, so here we did this with 3 pegs, and we were pretty sure just by doing it that 2 to the n minus 1 was the minimum number of moves. But how do we know that that's the minimum number of moves? Well, that's actually a pretty tricky question. So, a variation of this is, what about if you had 4 pegs instead of 3? Do you think we could solve the algorithm or solve the problem faster than if we only had 3 pegs? Probably, right? And we could sit down and maybe come up with a solution that would do it. Um, but the solution like that you come up with, and maybe like let's say I lock you all in individual rooms with no internet connections until you come up with a solution. Okay. Well, it's possible that some of your solutions would be more efficient than others. Maybe by dumb luck, you guys all get the exact same efficiency of solution. Maybe, who knows, right? But how do we know that there's not some really, really clever way of doing it, like buried in a book in the library that none of you guys stumbled on? We don't really know that, okay? And it wasn't actually until 2014 that the algorithm that was suspected to be the most efficient was actually demonstrated to actually be the most efficient, right? 6 years ago, right? For this stupid puzzle that's been around since the 19th century. Well, it's not really stupid, but whatever. Okay. Um, all right. Uh, Now, probably one of my favorite variations of it is this one. Okay, so this was first, uh, this particular puzzle was given in basically um, a French math competition uh, that would have been for like, I think, ninth and 10th graders in the 80s. Okay, now they gave it for specifically for 4 discs, but it's actually, in a sense, 8 discs. Okay, so here you have 2 pegs and then the third one as temporary. But the rules are that you start with 2 sets of discs. One set is black, the other set is white, but then they're arranged alternately so that um, the you've got white, black, or on the other set, black, white, white. Okay, and the object of the game is basically to sort them so that you have all of the black ones in a pyramid, just same thing, where they've got to go up in order, and ditto with the other ones. And that, as it turns out, is exceedingly tricky. Now, I gave a variation of this once just to see what people would come up with, where you did this, where you had 4 pegs. Okay, but here's the evil part. The bottom peg on, or sorry, the bottom disc on peg A is white, and the bottom disc on peg B is black. Okay, fine, whatever. We didn't really matter. The solution required is that you have to get all the white ones here and all the black ones there. Okay, so the bottom discs have to move, and this is what it should look like when it's all said and done. Having to move that bottom disc makes a significant challenge. Um, there is also, I should add, one change to the rules, which is, so now I have how many discs of each shape or of each size? 2, one black, one white. And I've seen variations on this too, as to whether or not you're allowed to put equally sized black and white discs on top of each other or not. Okay. I've seen both versions of it. Yeah. So anyway, so this was here it is. Uh, grade 3 through 6 students, which in the French system, um, they order the grades the other way. So grade 1 is, I think, the like seniors, not like kindergartners, right? Because I mean, imagine giving this to 3rd through 6th graders here in the U.S., right? um, anyway, so yeah, and I think actually it's got a link to this. Um, yeah, anyway, so here's a paper about it with all the algorithm stuff if you're interested. But anyway, okay, so there's that. Um, how many of you guys have seen Planet of the Apes? Okay, this does actually appear in Planet of the Apes. Um, here it is. Did any of you guys notice that or remember it from the movie? Hmm? Yeah, this is one of the new ones. Sorry, not the old one. Okay, but yeah, so this does appear in a bunch of different stories. The one I thought which was hilarious is this one here is that there's a puzzle in this game. I'd never heard of it to unlock a tomb, and you go and it takes 32,000 moves, and then it doesn't actually unlock the door. I would be so angry if I went through all of that and then didn't get whatever stupid reward was behind the door. Um, yeah, so uh, I've never actually heard of this game, but is it? Yeah. Okay. Well, so it's hard. Yeah. Okay. Well, I'll have to look it up on Steam tonight. Maybe have a little bit of fun. Okay. So yeah. So there's lots of variations of this. This I thought was pretty hilarious. Is that they used a variation of this on Survivor, and that seems like a little high level for that kind of TV show, but whatever. So yeah, and then of course the other hilarious part is that the uh, the Thai version of it, they of course know exactly what to do, and then when we give this to stupid Americans, they're like doop de doop. So you guys could win Survivor because of CS101, right? So that's pretty mad props. Okay, all right. So let's talk a little bit more about recursion in a more general sense. So if we go back to our code, right, what makes this recursive is that it's a function that makes reference to itself. Okay, so how do you unwrap the recursion? If I asked you by hand to execute this, say for example with the num disks equaling 3, okay, to get that sequence of prints, what would that look like? So let me actually go back to here just because it's a little easier to read. Okay. Um, all right. So if I were to ask you to execute this by hand for, let's just do it for say 3, then how would you sort of do that? Well, so if I asked you what's Hanoi of 3 A, B, C, okay, you would say, all right, num disks is 3. My start peg is A, my end peg is, oops, end peg is C, my temp peg is B. Great. Is the number of disks 1? No, it is not. So I'm going to do this instead. I'm going to do Hanoi of how many disks? 2 from A to C, or sorry, A to B via C. Then I'm going to move 1 from A to C. And finally, I'm going to do Hanoi of 2 from B to C via A. Okay, so this instruction means exactly the same thing as those three instructions. Okay, good? Yes or no? Okay, well, what does Hanoi of 2 comma whatever whatever mean? What does this mean to do? Well, now we're running back through, so I'm here, where numdiscs equals 2. Is that equal to 1? No, of course not. So I'm going to come down here and I have to do, so what's numdiscs right now? 2. I need to do Hanoi of 1. Oops. From start peg, which is A, to temp peg, which is B, via the end peg, which is C. Then I need to move 1 from A to C. And then I need to do Hanoi of 1 from B to C via A. Okay. So these three instructions are the same as that dude there. All right, what do we do after those? What do we do after Hanoi of 2ABC? We do a move. Okay, so this guy goes in the middle. And you know what? Let me actually do this. Let me use some tabbing to kind of indicate the okay, so here. Okay, so these three instructions, this instruction here is really these three instructions there. Okay, so we're peeling the onion one more layer. All right, Hanoi of 2A or 2BCA at the bottom, what is that really? That's Hanoi of 1 from where to where to where? Okay, who's my start peg? Or I'm sorry, I want this guy here. B is my start peg. I'm going to end where? C, using A as temporary. Okay, and so what that means is that here I've got, let's see, start was B, temp was A, and end was C. All right, then I need to move 1 from start, which is B, to end, which is C. And then I've got to do Hanoi of 1 from temp was C, end was, no, temp was A, end was C, with B. Yeah, okay. All right, so I've unwrapped it one more level. Okay, then the last step is, now look at what I have. I have a bunch of, in this case, 4 commands that are Hanoi of 1. Well, in all of those, which part are we going to use out of our definition? We're going to use this guy, right? Because now we've reduced it down to the n equals 1 case. Okay, so what is Hanoi of 1 ABC? That's to move from A to B. Do we need peg C in that case? No, we can just ignore that. Okay, and so what we're going to get, right, is move 1 from A to B, then move 1 from A to C, then move 1 from B to C, oops, then move 1 from A to C, then move 1 from B to A, then move 1 from B to C, and finally move 1 from A to C. Okay, and does that work if we sit down and we move those things? It would give us a solution. Okay. All right, so you see how kind of I unwrapped this thing, right? That's the kind of approach you want to take for for these sorts of problems is sort of try and unpeel it like an onion. And in the case of the exercises that you'll have on Canvas for this, it's not the Towers of Hanoi puzzle. Okay, so instead of moving or doing whatever, we'll have it where it's doing like some sort of arithmetic. Okay. Now, good example of an arithmetic operation that's defined recursively is this guy. What is this function? Okay, so if I asked you, for example, what is 3 exclamation mark, that doesn't mean to shout 3 really loud. Okay, what does it mean, Ethan? Right. Okay, so the factorial function is what that's called, right? And what it means is 3 times 2 times 1, or if you had, like, let's say 10 factorial would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So you multiply all the numbers down to 1, starting with whatever you're given, okay? This is an example of a recursive function because I could define it this way. I could define this like so. Well, let me actually write it like this. It's defined like that. Okay, so what is 10 factorial? Well, it's 10 times whatever 9 factorial is. Well, what is 9 factorial? 9 times whatever a factorial is. Well, what is a factorial? Right? And so on. And then eventually, what do we hit? Well, then we'd hit, well, it's 2 times 1 factorial. And what's 1 factorial defined to be? 1. Okay. Now, this is sort of annoying. What's 0 factorial? I mean, I've defined it here, but it's not. We define it to equal 1. Now, you might say, Dr. McKinney, you're smoking something, and may I have some, because that seems silly. But here's a good reason why to make that definition. All right, Ethan, let's suppose that you're picking out your outfits for next week. You have 5 t-shirts, and there are 5 days in the week, the work week. And let's further stipulate that Ethan, being a pretty stand-up guy, is not going to re-wear a t-shirt because that would be gross, right? You can do that with blue jeans, but not shirts for some reason. All right, so how many different orderings are there or different configurations of his outfits? Well, how many choices does Ethan have for his shirt on day 1, on Monday? Okay, on Tuesday, on Wednesday, and so on, right? Okay, so that would be 5 factorial, which happens to be 120. Okay, fine, whatever. Well, how many different arrangements of outfits would there be if Ethan had 0 t-shirts? Well, there'd be precisely 1. He has no t-shirts. Well, I guess in our previous problem, yeah. Yeah, so how many different ways are there for Ethan to arrange 0 t-shirts in an order? Okay, so like let's think of it this way. Ethan could choose the order of his shirts on Sunday and say, okay, I'm going to wear this t-shirt on Monday, that one on Tuesday, and so on. And there would be 120 different ways he could put those 5 t-shirts into order. Yeah? How many different ways are there for him to put 0 t-shirts into order? Well, there's exactly one way to do it. He has no t-shirts, right? There's only one thing that he can do, which is absolutely nothing. Now, is that why 0 factorial is 1? No, but that's kind of how I like to reason through why that it makes sense, okay? All right, so this is an example, oops, and this should be, yeah. This is another example of a recursive function. Now, the factorial is interesting because I don't have to define it recursively. I could have defined it iteratively, okay? Because how did I originally define it when we said it? I said you just multiply all the numbers down to 1. I could have written that as a for loop or a while loop, okay? But I could also think about this one recursively. Recursion in programming is dangerous, but sometimes it's really useful. It's dangerous in the sense that, well, what happened when I tried to get Python to do Hanoi of 1,000? Yeah, basically it croaked, right? And it croaked because I was hitting basically a maximum recursion depth. And the reason I hit that is because there's only so much memory in my computer. No matter how good of a computer you have, even your big supercomputer, right? It has a finite amount of memory, so you can't recurse forever. Um, all right. Well, we should quit and post some new problems and stuff for you guys on Canvas, and have excellent weekends. Oh, yeah, I can't. Okay, I think. Sorry, guys online. I just saw those messages. Um, yeah, my bad. You didn't see the Python. Okay, that's terrible. Crap. All right. Well, I'll put the code up on Canvas or something. So, all right. See you guys next time.